All right, so today we're going to talk about section 5.4. So this is predicated on the idea that you have read 5.1, watched the 5.2 video, read 5.3 before watching this video. So there are three main characteristics of a geometric experiment. The first characteristic is that there are one or more Bernoulli trials, or binomial experiments, as we might remember from 5.2, with all failures except the last one, which is a success. In other words, you keep repeating what you're doing until the first success, then you stop. For example, you throw a dart at a bullseye until you hit the bullseye, a success, so then you stop. If, for example, it takes 6 tries until you hit the bullseye, you can think of the trials as failure, 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 success, and then you stop. In theory, the number of trials could go on forever, and there must be at least one trial. For instance, you could theoretically keep missing the bullseye forever. The probability P of a success and the probability Q of a failure is the same for each trial. Notice this doesn't say that they are the same as each other, right? P and Q are not the same necessarily, but P is the same for every trial and Q is the same for every trial. For example, the probability of rolling a 3 each time you throw one fair die is 1/6. Well, if we find the probability of getting the first 3 on the 5th roll, then we're saying that on the first 4 rolls, we do not get a 3. So here, getting a 3 is a success, not getting a 3 is a failure. So in this case, the probability for these first 4 rolls is Q, which is 5/6, because that's the probability of getting a failure on any given roll here. Using our multiplication rule for probability, the probability of getting a 3 on the 5th roll is 5/6 times 5/6 times 5/6 times 5/6 times 1/6, which is about 0.0804. Here we have a few formulas for geometric probability distributions. Let x equal the number of independent trials at which the first success occurs. P is the probability of success, and Q equals 1 minus P is the probability of failure. The probability that the first success occurs on the xth trial is P of x equals Q to the x minus 1 times P. So this is just the probability of getting a failure x minus 1 times, followed up by finally getting a success. For instance, if we're looking at 20 independent trials, then it would be Q to the 19th times P. The mean of a geometric distribution, mu, is equal to 1 over P. The variance of a geometric distribution, this is sigma squared, is 1 minus P over P squared. And that means that the standard deviation of a geometric distribution will be the square root of all of that. Let's look at some examples. For this first example, you play a game of chance that you can either win or lose. There are no other possibilities until you lose. Your probability of losing is P equals 0.57. What is the probability that it takes 5 games until you lose? So here, it might be helpful for us to define what is a success and what is a failure. In a problem like this, it can become very easy to get confused, I think. Our success here is actually losing the game. Right? We want to keep playing until we lose and then stop. So, in other words, we're going to keep failing until we succeed here. So this means that our failure is winning. So here we want to find the probability that the number of trials it takes would be 5. And this is going to be Q to the 5 minus 1 times P. I know that P is 0.57 because that was given to me. This means that Q is 1 minus 0.57. So Q is 0.43. This means that the probability that it will take 5 games until you finally lose a game is 0.43 to the 5 minus 1, which is 4, times 0.57, which is 0.0195. For this next example, a safety engineer knows from experience that 35% of all industrial accidents in her plant are caused by failure of employees to follow instructions. She decides to look at the accident reports selected randomly until she finds one that shows an accident caused by failure of an employee to follow instructions. On average, how many reports would the safety engineer expect to look at until she finds a report showing an accident caused by an employee failure to follow instructions? So in this case, our success, again, it's a good idea to identify what success means and what failure means. Our success here would be the report indicating that the accident was due to the employee failing to follow instructions. The problem tells us that this happens 35% of the time. So the probability of this success, P, is 0.35. Now, if I want to find out, on average, how many reports the safety engineer would expect to look at until she finds one such accident, I have to use my formula for the mean of a geometric distribution. This will give me the number of trials that have to happen on average for this outcome to be true, essentially. So mu is 1 over p. This is 1 over 0.35. And this gives us 2.857. You can't have 2.857 reports, so we'll say about 3 reports. We'll round up. So this safety engineer would expect to have to go through about 3 reports before finding one that indicates that the accident was caused by a failure of following instructions. A failure to follow instructions.